Good evening, everyone. I know I'm the last one, so I'll try to keep it short. My name is Midshipman Ryan Dix, and I'm a first classman at the Merchant Marine Academy. Done some research over the past year looking at the actual material considerations from fused filament fabrication, which is, oddly enough, the type of 3D printing that we heard about earlier today. Stratasys, which I believe you use the Stratasys machine, calls it fused deposit modeling. It's the same process, just protected or non-protected, basically. So just some introduction. What is additive manufacturing? Additive manufacturing is any manufacturing method that produces an object on a layer-by-layer basis. So on the left we see what's the most common, this fused filament fabrication, making a little toy Eiffel Tower. And then on the right we see a selective laser sintering process being used by GE currently in their LEAP jet turbofan engine, designing the fuel nozzle for those engines. So this additive manufacturing is being used actively today. If you fly on the new 737s, they have LEAP engines on them, and those have additive manufactured components. So you're already trusting the technology today. This fused filament fabrication is what I actually studied because it's the most common form of 3D printing, and it's the most applicable to shipboard use right now. The Navy has actually done a couple of studies putting these on board ships, seeing what that effect has on print quality, on part strength, and some other considerations. But we're still very much in the research phase, trying to figure out what these parts actually do, how they behave. The general scheme of how these machines work is that filament, the material, is loaded as a spool and then pushed through a heated nozzle here. That nozzle is controlled in the X and Y axis, typically by a series of belts, and then in the Z axis with a power screw. So you just kind of print one layer, move it down a step, print another layer, move it down a step, and 20 hours later you have your part. Which sounds like a long time, but you don't have to do anything for that 20 hours, so it's nice. Taking a look at additive manufacturing in the maritime industry, we're not seeing much onboard ships right now. Again, the Navy did the print the fleet, kind of sent out some feelers to see what people could come up with. There wasn't a ton of research done there. The Marine Corps is actively using this though. This is a containerized system inside the container of a Marine Corps X-FAB unit, they call it. They have two different, and there's a third one in there, but these showing two different fused filament fabrication machines printing up. This is a little visor cover for one of their light attack vehicles, and then they have some other just small tidbits to show how things work. They also actively print drones for surveillance usage. So this is being used actively by the Marines and really going very well for them. They have a great system for coming up with what people can actually print, because there's obviously concern with just going out there and making something and bolting it to the ship without really knowing how it's going to work. The Marines came up with a system where they have the files for printing, not the CAD files, the actual files for printing, in 3 different folders. A green folder that anybody can print at any time. This would be something to cause some common annoyance on board a ship, like you have a rolly chair and you need solid feet for it so it doesn't roll across the control room. Or a doorway catch, something simple like that that's not really going to affect the structural integrity or the mission readiness of the vessel. A yellow layer, which is something that might cause some issues in a mission, but likely won't damage either Marines or their equipment. That would likely be something like this sun visor here, where, yeah, it's a pretty big object, it's going into the mission, but it's not actually sustaining any load really, it's just blocking the sun. Then they have a red file that has to be approved by Marine CENTCOM, so it's very high mission, critical components that basically if we don't print this thing, we can't get home, or we can't get our Marines home anyway. So the logic is we have to get home, we might as well make it with this 3D printing, see if it works. The other side of things is rethinking some supply chain issues that are currently in shipping. What sometimes happens with spare parts for vessels is that you end up with the spare parts kind of chasing the vessel around the port because you can't ship faster than the ship is shipping things. because you're on a ship shipping things, it ends up being a big headache. With 3D printing, we can just take raw material into a facility and then have all of those components produced in that facility and just brought by a local van right to the ship. So you have this small facility, you know, probably about the size of this room, that prints out your cylinder liners or your fuel injection valve components. You assemble it, bring it right to the ship, and you're good to go. The nice thing about this is that it would keep the intellectual property in the hands of the engine manufacturer or the pump manufacturer, whatever the case may be. You're not sending the files anywhere, you're managing that process, so you still have all that intellectual property. The bulk of my research was in the actual material considerations of this fused filament fabrication process. You know that anytime we change how a component is made, how that component is manufactured, we change its material properties on the outlet end. So talking about cold rolled steel versus hot rolled steel, there's a difference there in material properties that we understand for steel. We don't yet understand it for most of 3D printing, and specifically for this fused filament fabrication that's applicable on board ships. So just a general overview of my abstract, we see that this fused filament fabrication is the most successful. It's commonly used every day, being used right now for functional components, and it can be put on board a ship just as simple as, you know, the first engineer going out and getting one, basically. Two major difficulties arise when researching the properties, and they basically come out to the amount of control the user has over the printing process even after the part geometry has been specified. So typically when we're designing things, we know the part geometry, and that gives us a direct correlation to how that part will perform under load. With fused filament fabrication, we can't say the same thing because there's so much control left to the printer operator, not to the actual design engineer. And then there's a clear lack of standards surrounding all of 3D printing and fused filament fabrication in general, that we ended up using an ASTM standard for polymers, not for 3D printed polymers. And again, looking at how something's injection molded versus how something's 3D printed, those are two entirely different processes that have different considerations. So we took a test specimen from that ASTM standard. It's ASTM D638, which is standard tensile methods for polymers. And we studied that geometry to show how much we can change just in one geometry, and then figure out what some of the correlations we're looking at there. And ultimately, we came up with a method for predicting component strength in ultimate strength, yield strength, and modulus of elasticity. That's fairly accurate, and it's at least a starting point. So my methodology here was to test the commonly altered internal structures of a 3D printed component to determine how they correspond to load and how they deform under load and how they keep moving. So on the left, we have the infill percentage, which is essentially the amount of material inside an actual component. And that can be as low as 0% and as high as 100%, although even 100% still has some voids in there. It's more like 99% by density. So there's a practical lower limit that 10% is just about as low as you want to go, otherwise you run into some just difficulties actually finishing the print. Next we moved on to the number of walls here. It's kind of tricky to see, but here you see one blue line, this one has 2, then 3, 4, and 5. And the number of walls is less frequently used than the infill percentage when users are trying to make something stronger. It's pretty simple to think that if you put more material into something, it's going to be stronger. So people default to that infill percentage. Number of walls in some different circumstances, particularly flexure, you're going to see a higher strength increase from increasing the number of walls. Then lastly, changing the actual shape of the infill. So most people will just stick to the standard grid infill shape because it's easiest, it's what's already set. There's also a triangular shape, so it's easier to see over here where you have a series of triangles being repeated. And then lastly, this combination infill shape, which is essentially a grid infill shape overlaid at a 45-degree angle to each other on a layer-by-layer basis. So you have a grid this way, and then a grid that way, and a grid that way, a grid that way, just repeating up. Some of my collected data, again, we tested as per ASTM D638. It's a standard tensile property, so these are all tensile properties for that polymer. This is for the wall thickness, and we see linear increase as we increase the thickness of the wall in all ultimate strength, yield strength, and modulus of elasticity. There's not a huge correlation in terms of ductility. It's really, we're not seeing much correlation there. But we do see some pretty interesting effects in the stress strain curves. We start off with a very characteristic, a very polymer-like start off to the stress strain curve, with actually a microstructure property showing through in our final structural form. Most of what we're looking at is structural in terms of it's the infill shape, it's how these things are actually being printed. But this toe region here is actually a polymer property where you have these microstructures unfurling to align with the load and actually lock in place once they're there. Then we see the actual curves themselves look fairly nice. One wall here and two wall don't really curve down the same way as 3 wall, 4 wall, and 5 wall do, which points to a stress concentration being added in the later ranges of that ductility. And you're seeing the effect of the infill pushing against the wall and then causing a stress concentration to form and early failure. With 3, 4, and 5, the wall is just thick enough where it can basically push back against that stress concentration, and it'll neck nicely and then fail like you would expect from a metal specimen. Next we have the infill percentage data, and this shows an exponential increase as we increase the infill percentage. So really we have 3 main groups, at least the way that I see the data, and that I'll be going forward with my own 3D printing and testing and whatnot. We have below 60%, which is really good for prototyping when you don't want to waste material and you just want to make sure that something works. Then you have 70 and 80%, which are okay, they work, but it's really probably smarter to stick to 90% actually. 100% is higher, but we see that it fails relatively early compared to the 90% one. It has a relatively low toughness. I should start at the start. We do see the toe region again, so that's a material property of the actual plastic. It's not really a structural thing. Then we have these lower ones, so below this line here. Again, they're all failing pretty early without seeing the full stress strain curve develop. For 70% and 80%, we see really good ductility, really good toughness, that they're really able to deform and continue carrying a high load for the entire time, right up until they fail at the last minute there. 90%, the same story, but you have a significantly higher ultimate and yield strength because the curve is just able to shoot up faster. You have more material there. 100%, again, it shoots up faster, but it fails earlier. This is likely because when you have less material on the inside, the voids don't act so much as stress concentrators as they do allowing the material to actually move slightly and actually deform around that load. So as you put it under load, all those little holes, which are normally square, become little diamonds, and then it's able to continue sustaining that load. With 100%, you just don't have that space, so they act as voids. They create stress concentrations just like any other void, and then it fails earlier. Lastly, the infill shape, which is by far the oddest of the graphs. Starting with grid, which is the standard shape, again, we see the toe region. Still, it's a polymer property. It's not a structural thing. That's always going to be there for these samples. The grid infill shape, which is the standard, really just underperforms. There's no other way to put it. It has the lowest of Young's modulus, yield strength, and ultimate strength, and just that's all there is to say about it. It's the standard, but it shouldn't be the standard. The triangle shape has a high modulus, and it's likely because we're talking about 30, 60, 90 triangles, which can lock into place a bit more compared to the 45-degree angles and 90-degree angles of grid and combination. And then combination shows really what we would expect from most curves like that. So combination is great when you want all-around good properties, and that triangle is great when you want a really high Young's modulus. All that data is great, but without being able to use it, it's just data. I came up with this formula for actually predicting the part strength based on essentially the principle of superposition. So we have the design property, P sub D, which is a function of the material property, so the actual material you're printing with, a derating factor, KFFF, which basically takes that material property, says, okay, we're 3D printing it, so it's going to be a little bit less strong. That was calculated just by finding the strength of a 100% sample and dividing it by the strength of what we should expect from that material. So it's just saying, okay, 100% isn't as strong as 100% material. That's how strong it is. Let's bring it back down to the base level there. Then we have this A sub W over A sub X. The A sub W is the area of the actual wall layers. So now this term here is the actual superposition. You see that the strength is going to be a function of the strength of the wall and the strength of the infill structure. So the strength of the wall is going to be the material strength derated to be 3D printed times the area of the wall compared to the area of the actual material we have. That's pretty straightforward because the wall is 100% material. We don't have to apply any other factors there. For the infill structure, it's a little bit more complicated because we can change all those factors. So we have the area of the infill over the cross-sectional area. Then we have a factor for different infill percentages. So, you know, if you have 40% infill, that would be 0.2060, and that just says 0.206, or 40% infill is 0.2 times as strong as what we should expect from 100% infill. So that is another derating factor saying, okay, we have to take now this material property, derate it again because we only have 20% of it there. And then another factor for the type of infill we have, saying, okay, now we're using grid infill, and all of the tests were at grid, so that factor is just going to be 1. But if we're talking about combination, it's 1.9 times as strong as grid, so we have to kind of go back up and say, okay, you're doing combination infill, so it's stronger than we would expect from grid infill. So relatively complicated. I don't have the actual data here, comparing some more recent tests we did looking at basically random samples of different specimen and seeing how closely the formula aligns with the specimen. It's about 20% of the way there, which isn't great, but it's better than guessing and checking and guessing and checking and guessing and checking. So in conclusion, additive manufacturing can completely reshape how we design and how we manufacture components onboard ships, offboard ships, bringing it right to the ship. But it's not really that well understood, and we don't know the material side of things, how they actually respond under load. Fused filament fabrication is the largest and most applicable form of additive manufacturing, but the components are just unreliable. Some person could print the same component as somebody else. One might fail, one might not. We still don't have a ton of information as to why that is. I tested the properties of some specimen to determine how they actually change due to some common structural changes, and then came up with a method of a semi-empirical formula to determine how that actually plays out in the real world. And I'd love to hear any questions. Yeah.
So I mean, one great. I worked a lot with 3D printed stuff. It was always like, as you say, guessing, checking.
Yeah.
I'm surprised I didn't have a resource like this already, so we've had it for a while. In terms of the applications of ships, I think your equation is very good, right? It's when developed further, it's going to allow us to predict a fair amount of metrics for the strength of these products, given the different parameters. Have you considered at all the potential for including this in some sort of software where instead of using these options as a manual input, you can override the system and simply, along with the code for the part, include all the preferences you need to include, temperature, the nozzle, and things. It's definitely a software piece that would overcome this kind of uncertainty factor of user inputs.
Yeah, so some more advanced machines, specifically once we start talking about metals, you don't actually put in the G-code file, which is the toolpath command file. you put in the CAD file, and then you select all of your options like on a human-machine interface on the printer. That would be nice for 3D printers. It unfortunately drives the cost pretty high up because you have to have a processor inside. Yeah.
Yeah, I'm talking more about a software solution that you can link to code part. It's not necessarily developers who we know about, but
Yeah.
I really like your
Thank you.
I think your approach here on looking at the manufacturing process, making the parts, and then testing for obtaining properties is really good. And I was just thinking back on when composites were first coming into the market, that people would rely on the strength and stiffness of a fiber and not a laid-up fiber with varying thickness where the properties degraded quite a bit. And you really seem to be addressing that point. So it seems like a very good approach.
All right. If there are no other questions, then.
Thank you.